So does everyone have this course material? So the plan is we're going to do wavelet theory, and basically the way we're going to evaluate everyone, I don't want any pressure on anyone. The idea is just to learn, and so there is a set of exercises that's I've written down, I don't know, 20 or 30 of them so far, maybe more, but anyhow, quite a few. And I shall assign exercises every class, 3, 4, 5. But for the term, what I'd like to do is pass in maybe, I haven't thought of a number yet, say 20 of them. And also, let's pick a project that you're all very comfortable doing. There are lots of topics that are going to arise during the course of the semester, and I hope to reach the stage where we can talk about current papers in the field. And so, basically, I'd like to have you find one of those topics that's appealing to you, and at the end of the term, pass in a paper describing the paper you've read or something to that effect. So basically, there'll be no in-class tests per se, but I do want you to do these problems because there's no better way of learning mathematics. And plus read something that's relatively current and that you find very interesting, and show me that you've understood by getting it back. Okay. I've used this system for a number of years, and I think it's basically effective. Now, on this course material, we don't have to go through the whole thing now, although we'll cover most of these topics. But for the first lecture today, I am going to use what's called the introduction here. So several people have come in since it started this. Who else doesn't have one of these sheets? Pass that. I will. Okay, very good. So I'd like to have a level playing field. I know there are a couple of people whom I know that know everything. First couple of topics here, but my goal is to have everyone learn everything and well. Today I'm going to talk about what is named introduction here, namely real analysis, a little bit of history and background, although we'll do a lot of that every class. It's the first thing I have meaningfully tell you about the history right now. And perhaps the most important thing today is number 3 and 4 there, where I talk about the sampling theorem and the Poisson summation formula, because those two items are very relevant topics for a natural segue into wavelet theory. Now, I saw, I don't have all the names yet, but I did see the list of names and what schools you're in, what program you're in. And so, just to let you know, I know some of you might be more interested in pattern recognition or image processing. And by the way, we do that here. I mean, we're associated with the Norbert Wiener Center, which has some very applicable programs that we do. But I'm going to treat this time around as a mathematics course and try to really lay the foundations of the subject. I believe ultimately that gives you the background that gives you better flexibility when you really want to use the subject. So I've done it several ways through the years, but this time around we're going to do it this way. Let's see, what else should I say before getting going? As far as the history goes, I'll probably be repetitive, but on the other hand, I find the history of the subject fascinating, because it's in some sense been with us since late in the 19th century, and certainly in the early part of the 20th century, some basic theorems in the subject were proved, but not realize that they were really what is now Wavelet theory. And things came together in I'd say the late 1980s. Well, there had been significant work related to it just a little before that. And what was happening is that a lot of the folks, people in, by the way, I'm lisping a little bit because I fell recently. I'll be speaking much better as the semester goes on, I hope. But a lot of folks from various fields found out they were doing very similar things. For example, people in speech processing and were dealing with conjugate mirror filters from the 1970s. People in image processing were dealing with pyramidal schemes. And people in mathematics were dealing with things known as the Calderon reproducing formula and other types of bases expansions. And it turns out there was a common thread. And in some sense it was discovered accidentally over a water cooler. That's not even a joke. And by the late 1980s, a number of very clever people got together and realized some of them were doing very similar things. And Wavelet theory emerged as more or less a theory on its own, with lots of relevant applications. There was a period in the, I'd say, early 90s when people thought it had replaced sliced bread as the world's greatest discovery. But Wavelet theory is a very nice theory. It solves some problems, and it doesn't solve other problems. But it's a very important theory. Okay. So I'm going to begin by reviewing some things we need from real analysis. And in some sense, you don't need, not in some sense, but you do not need the Lebesgue theory for this course. It's nice if you've had it, but it's not a sine qua non. Because I'm just going to say L1 is a bunch of functions that you can integrate, and you can think of whatever you remember about integration. I'm looking at Nate Strawn right now. Nate, I sent you some exercises today. I'm not sure if you checked your email in the past few hours. What I'd like each of you to do, Nate now has a PDF file with the exercises I've written down so far. So I would like to have you each send your email address to Nate, and he will send you a PDF of these exercises, because I'm going to assign some today. Okay? So, do you care to share your address in public, or should we do it by some sort of...
start illustrating.
I'm sorry? No. Oh, you're just going to pass it around?
Yeah.
As you like. I was just going to write down your address up here and make you all copy of it.
Okay. Yeah,
So, tell me what it is, Nate?
just did Sean.
The chalk is very soft today. You're going to think I'm being very wasteful for the taxpayers, but it's just breaking in my hand. And Strawn. N-S-T-R-A-W-N. Okay? Okay, so let me begin by stating two inequalities, which are very, very useful, that we'll use all the time in this course. And one of them is called Hurl's inequality. And it says the following. If 1 is less than or equal to p is less than infinity, I can actually take less than or equal to infinity, but let me just state it for the just in case now. And 1 over p plus 1 over q is equal to 1. And f belongs to LP of R, I'll define momentarily, and q belongs to LQ of R, then f times g, that's a g, not a q, then f times g belongs to L1 of R, And we have this following inequality, namely that the L1 norm of F times G is less than or equal to the product of the LP norm of F times the LQ norm of G. Okay, so what do those things mean? And so here's where I'm going to avoid directly using Lebesgue theory, but if you've had it, this is really the way I'm thinking. But all we're going to mean by, so this is just an aside here, F belonging to L1, well, let me do it this way. F belonging to LP of R means this number here integral over all of the real line of F to the P, 1 over P, sine. Okay. Now, where F is in this function R, taking complex values. And so this is a very standard inequality, and I've stated it for functions defined on the real line, but for those of you who've had measure theory, you know that this result is true when I use any measure here, not just Lebesgue measure or usual measure of distance. And it's also true over any measure space. But we're just going to be dealing with the real line here. But any of the difficulties we're going to run into, the subtleties of the subject, are all there on the real line and on Euclidean space. So, okie doke. Now, for those of you who've ever had experience with inequalities like this, what you realize is there's less there than meets the eye. Basically, it's a very nice inequality, but if you can't use it, it's very difficult to use anything more subtle, unless you can use some intrinsic issues of the problem at hand. In a different direction, but also slightly more sophisticated inequality is Minkowski's inequality. By the way, please ask questions. Okay? 3 hours is long time. We will take a short break if you want. Some of you may want. If you don't, just go straight through. But to keep everyone awake, keep me honest, ask questions. Minkowski's inequality is let P be bigger than or equal to 1. And let F be a function defined on the direct product of R with itself, taking complex values. And it says the following. Then the integral of the absolute value of the integral of F T U dt to the P du, and I'll take the P through to that, otherwise these inequalities aren't true, is less than or equal to the integral of F of T U to the P du, the 1 over P dt. Now, this number here, by the way, and I'll frequently drop the integral over R. So, integral for us, unless I say otherwise, is the integral over the line. Okay. So, this is looks like I just put integral signs and absolute value signs around wherever I wanted to. But it actually says something interesting. It says that an integral is like a sum, so let's think of that as a sum. It says that the LP norm of a sum, oh, it's this minute, actually, no, I did it right. The LP norm of a sum, that sum there, is less than or equal to the sum of the LP norms. Okay, so if I wrote that down just in terms of finite sums, that's what it would say. I'm saying it in a way, in terms of integrals, which has more power to it. So it says that the LP norm of the sum is less than or equal to the sum of the norm. Okay, now the greatest object of this course is the Fourier transform. Let's define that right now.
And that inequality is good for any measure space as well?
Yes.
Okay.
And really, any measure, take any measure, a discrete measure space, any arbitrary measurable measure space, it's true. I mean, basically, the proofs are very, very general.
So this doesn't have to be R cross R?
No, it's not.
X.
Correct. And then there are mixed norms in here where you can throw in P's and Q's. They can get rather baroque, but we will keep it unbroken. I'm going to blush for puns as it's being recorded. So the definition of the Fourier transform, the Fourier transform capital F, I'll use that, or I'll use F hat of the function F from R to C is a function is defined by for every gamma in R hat. Let me write it over here. Can you get over here? F of gamma is equal to the integral of f of x e to the minus 2 I x gamma dx. Okay, now the Fourier transform, Fourier lived in the first part of the 19th century. Yeah.
What do you mean by R hat here?
Let's say that. Thank you. Where R hat is actually equal to R, and the reason I'm being fuddy-duddy about that is I want to think of functions defined in the real line, but the Fourier transform contains frequency information, so I want to think of, when I'm thinking of the real line as a frequency domain, I'm going to put a hat on it. So I'm really I'm dealing with the real line in all cases here, but I want to think of my functions that I'm going to analyze, whether they be temporal functions or when I go to RD, spatial functions, and then I want to think about their spectral content. It's still going to be defined in RD, but I'm going to put or R, but I'm going to put a hat on it to think for that reason. Okay, just to make the distinction. Okay, well, I mentioned that Fourier, he certainly did analyze it. And he analyzed it in terms of some of these classical partial differential equations of 19th century physics, particularly. He analyzed the heat equation. But certainly in the 18th century, people like Euler knew how the Fourier transform worked and how Fourier series worked. Well, there's a remarkable fact that goes on here. And this is just a formal fact for now, but it says the following, that if F is the Fourier transform of little f, then, at least formally, f of x is equal to the integral f of gamma over r hat e to the 2I x gamma d gamma. The only difference here is there's a minus sign there and there's a plus sign there. So this baby, if I compute the Fourier transform of something, then the original function itself can be written down in terms of that Fourier transform. At least formally. This is not always true, this fact, this formula. But it's a remarkable fact. And it's one of the reasons, and I'll say why in more detail, it's one of the reasons why transform methods are still with us. Whether it's the Fourier transform, or the Hankel transform, or the Laplace transform, or the Radon transform, any of these transforms, it's because they usually have a very efficient inversion theory. And let me just say it briefly now, but I'll say more a little bit later. In the case of the Fourier transform, you might have some very complicated differential equation, and that's really what's called some sort of a convolution equation generally. And what you do is you transform that complicated equation by a Fourier transform into an algebraic equation. Now that can be just as hard, but it looks easier to us. We're psychologically ready to think it's easier. You solve that algebraic equation, and then you take the inverse transform. So this whole theory of solving complicated analytical equations, something like Fourier analysis, is very, very valuable. In Wavelet theory, we go a step further. Well, let me, I'm doing sort of a basic analysis here. I'm not proving anything. But let me tell you why that formula is formally true. And I come from Boston, as you may have detected if you haven't already. So you haven't heard any R's there. But one of those words had an R in it and the other didn't. So it's a, but let me tell you why that's formally true. There are two sort of natural phenomena that I'm going to write down in a mathematical way. One of these natural phenomena is, I'm going to call it the delta. I'm saying there's an object, delta, which has the following properties. By the way, this is all nonsense. Don't go home and tell your paramour that I've said some of these things because you know, I could get in trouble. But intuitively it makes sense. So delta says that for all f, so this is not precise mathematics, but it's what drives this particular formula, which is very useful to us. For all f, f of t is equal to integral f of u delta t minus u du. Okay. We're saying that there's some object, delta, that has this property. Well, if you think about what an integral is, forget Lebede's, your old Riemann integral. What that says is that there's some object, delta, which has very, very tiny support, 0 every place except, say, at the origin. And then it's so big at the origin that its integral is 1. Now, that is absolute nonsense, what I just said. But you can make it precise. And in fact, delta is not a function. Delta is actually a measure. But let's just say there is some object that has this property. Okay, there is. Now, of course, Dirac, who was one of the deepest physicists of all time, gets credit for this baby, the Dirac delta function. And it's neither a function nor is it due to Dirac. And because he did much greater things than this one. But he did use it. If you look at his old quantum mechanics book, I mean, you see he could manipulate delta with the best of them. The other thing I want to talk about, I want to say that this is I want to say what a formula is that would remind us of the uncertainty principle. Now, the uncertainty principle comes in many shades. And the one I want to write down now is the following, namely that delta of t is actually equal to the integral of e to the 2I t gamma t gamma. Okay, now some things I'm going to run over quickly, but this, which is absolute nonsense, I'm going to spend some time with, because I think I can share an idea with you. So first of all, this is absolutely meaningless. I said here it's not a function, and I'm writing it down like a function. We know we can't integrate over the whole real line exponentials like this without making some serious constraints. So what am I saying here? Well, before I tell you what I'm saying as far as this equation goes, I think this one has a little more meat. You can understand it better. Let me tell you why these two equations, if I can convince you they hold, would give validity to this inversion formula. So here we go. So I'm going to assume these two equations, which don't mean much right now, I admit. And let's write down the right side of that inversion formula. So the integral f of gamma e to the 2 I t gamma d gamma is equal to the integral of the integral f of u e to the minus 2 I u gamma. I've just written down what f of gamma is. E to the 2 I t gamma du by d gamma. Okay. So, by the way, I'm doing everything wrong. Everything that some math 410 professor tells you, you can't do that, you can't do that. That person's right, of course. But formally, I'm just writing this down. So that's equal to, let's just switch limits. We know we can't do that in general, but let's just switch limits. This is equal to the integral of f of u e to the 2 I t minus u of gamma d gamma du. Well, this is equal to the integral f of u. And then I have this integral e to the 2 I t minus u gamma d gamma du. So by one of my fake equations over here, this is just equal to delta of t minus u. And that's the uncertainty principle equation. And then that's just equal to f of t. So if I can sell you these two bridges made in Brooklyn, then we formally see that that inversion formula for the Fourier transform makes sense, has some meaning. Okay, so as I say, this one intuitively you can sort of say, well, if there's a skinny little function that's really high, integral 1, maybe something like that makes sense. And if you take measure theory, you can define that delta measure. But how do you make sense out of this? So one way, when I was wrestling with this years ago, was I thought of, well, what if you take a piano that has the right number of keys on it, and you look at the A above middle C. That has 440 vibrations per second. So if you go down an octave, it's 220 vibrations a second. Go down an octave, that's 110 vibrations per second. Go down an octave, that's 54 vibrations per second. Go down an octave, are you still on the piano? Yeah, you are. That's the bottom A of the piano. You get 27 and a half vibrations a second. So what if you have this fantastic dexterity, and you can nail that key, and the key strikes the string, and you do it for 1/30th of a second. And then you let it up, and the mechanism of the piano is spectacular, and it goes back, and when you let it up, the sound stops. But that thing, to get pure sound, it has to do it, it's 27 and a half vibrations a second. So if you've done it faster than that, which I just claimed I did, then you don't get a pure sound. What you get is noise. And what you get when you noise in this form is you're essentially adding in all the pure sounds together. And so what you're saying is that if you get really good temporal localization, then you cannot get good frequency localization. You're essentially summing over all frequencies. So I'm really talking with my hands. My Italian heritage is doing well here right now. But that's the idea. And it's a very profound theorem, because sometimes it's true. And the reason it's true is that you can make precise some of these ideas. So I wanted to spend a little extra time with that because it's something we use all the time. And here's one theorem where it is true. So I'm going to write down the statement of the theorem which is precise. So theorem, inversion formula. So let F be in L1 of R. Assume F hat is in L1 of R hat. That's not always the case. And assume F is continuous on R. And these two conditions in the first line do not apply this necessarily. It's just that it holds almost everywhere. Then we have the theorem. Then for every t in R, f of t is equal to the integral f hat of gamma e to the 2I t gamma d gamma. Awesome. Okay. Now, I'm not here to advertise any of my books or anything, but these results, if you're not familiar with Fourier analysis, you should look at some book on the subject. There are a zillion of them. Many of them are very good. The one I know best is the one I wrote. I'm not saying that's one of the very good ones. It's the one I know best. And so I encourage you to look at some book on the subject. My particular book is called Harmonic Analysis and Applications. And perhaps next time I'll get a list of books, not only on harmonic analysis, but on wavelet theory in general, to Nate, and we'll distribute that list the same way. Okay? Okay, so just generally speaking, transform theories have, even though we're doing analysis, we're integrating, blah, 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 blah. One of the reasons they really work, besides the reason I said about differential equations, is that frequently they have an underlying geometric or algebraic structure. And the Fourier transform is perfect in that sense. It has these invariants, namely things like translation. For example, translation is something you would really want in physical experiments. You'd like to be able to, if you had an experiment on Tuesday at 3 o'clock in the morning, you'd like the same result to hold on Friday at 5 in the afternoon. Now, that's not going to be the case in astronomy, but in a lot of lab experiments will be the case. And that's one of the good things about Fourier analysis. It has very good translation properties. It has good rotation properties. And has good dilation properties. I'm not going to write all those things down because it takes time. But let me, just for notation, we're going to use dilation a lot in this course. That's one of the things we do in wavelet theory. But there's a lot of translation and dilation and modulation. So let me define the following dilation. So we have a function f with definition given function f defined on the real line. let lambda be a positive number. And I guess I just want to take F and L1. Find F lambda of t to be equal to lambda F of lambda t. Okay, so that's a type of dilation. Then a remarkable thing happens, namely, then, this was a definition, but now we have a fact, that the Fourier transform F lambda hat at gamma is equal to F hat of gamma over lambda. Now, the way of thinking of that is what it is geometrically. What it says geometrically is more or less remarkable. It says that if, because of the lambda we use here, we are really looking at a function f lambda, which is supported in, is mostly in a little small interval, then when we take its Fourier transform, we're going the other way. That means it's really spread out. That is exactly what our uncertainty principle thinks of over there. Here we have, this is elementary to prove, and it's true. Over there, we were using it as a motivation to get a formula to work. So what really goes on in Fourier analysis is, if you've squeezed a function into a small interval, and you take its Fourier transform, then its Fourier transform is going to have a lot of big spectral content at Beach Avers. Now, there are different types of, here I've done this because this will preserve the L1 norm, but we'll also use it with the L2 norm. And so let me just write down for our convenience another one. So, for example, if we use the notation F going into its Fourier transform capital F, and then what happens for L2 norm is that we have lambda for the 1/2 F of lambda t actually has its Fourier transform lambda to the minus 1/2 F of gamma over lambda. So it's basically here the L1 norm is preserved, and here the L2 norm is preserved. It's the same phenomenon. It's the same uncertainty principle phenomenon. Okay, another piece of notation that we'll be using throughout, which I'll do in terms of the dilation, is the sinc function. Now, the sinc function is sine of pi x over pi x. I'm going to use a slight modification of it just because it makes this dilation trick work better. So if I take the function, for example, that, now, I hope you can cut out the yawns in the audio, because otherwise people will think I'm putting them to sleep in droves here. So I have to do some noise reduction in this stuff. So let f of t equal the characteristic function from minus t at t. So all I mean by that is this nice square wave. 1 there is minus t minus t. And then, if I just take the Fourier transform of that guy, a direct computation shows, even though this is not good board style, I'm looking at that function, but let me go over here and compute its Fourier transform. then Fourier transform at gamma is actually equal to the sine of 2 I t gamma over pi gamma. And so what that means is, I just computed out. I mean, you can sort of see that with the definition of the Fourier transform. So therefore, set d of gamma equal to the following function: sine of gamma over pi gamma. Then what is d? What is the dilation d2I t of gamma? Well, by our definition, it's 2I t d of 2I t gamma. So that means with d of gamma being this, it's the sine of 2I t gamma over, and I've got a pi and a 2I t gamma, and I'm multiplying it times a 2 pi t. And so I get this guy here. So I want to use this notation. I want to use this notation. D of gamma is equal to sine of gamma over pi gamma. And then if I do that, if I compute the Fourier transform of that characteristic function, that's the guy I get. Now, the reason I'm using D, and you're saying, gee, that looks like the D of gamma in an integral, I realize that obfuscates things a little bit, but the reason I'm using that D is this subject got a true boost. In particular, this function got a true boost from Dirichlet, who preceded Riemann, the chair preceded Riemann in the chair prepared him, and he did some of the initial work on the conversion theory using this thing function. Okay. Now, another function which we'll use significantly is the Gaussian. And so let me write down the Gaussian.
Was that a 1 used for the characteristic function?
Yes, this is in LaTeX it's math BB.
Okay.
You want to make it in LaTeX. I actually like these things with the double lines.
Okay.
As opposed to bold. So a very important function which we also use a lot, Gaussian. And basically, let's look at a particular form of it and do a computation. So let's take f of t equal to e to the minus pi r t squared, where r is going to be some number bigger than 0. So compute f hat. And basically, to take the mystery out of it, let me just write down the answer first. Well, if I can't find it, I won't write it down first. I'll just compute it. So the Fourier transform of this guy is equal to 1 over the square root of r, and then e to the minus pi gamma squared over r. So that's the computation I want to do. By the way, notice again, we have this uncertainty principle phenomenon going on. I mean, it's just what the Fourier transform does. If you've got something squeezed on the temporal side, it spreads it out on the spectral side and vice versa. And this whole concept of spectral synthesis as it relates to the uncertainty principle is very, very complicated. And I'm not even showing you a hint of it right now tonight, but this is a hint of it, I should say, but the complexity of it is rather profound, I would say. But why is this the uncertainty principle? Well, basically, if this guy here, if that R is such that this thing here comes down very quickly, I mean, you all know a Gaussian is going to look like this, but the same look, this one looks like this, and it comes down quickly, and then depending what R is, this will just spread it out a lot farther. It'll come down and take a lot longer to get down. Okay.
So Fourier transform of the Gaussian is just another Gaussian.
The Fourier transform of the Gaussian is just another Gaussian. Yeah, children of human beings are just another human being. And it's really so tedious. But you know, there's and having children there's a lot of uncertainty involved too. So so why is this calculation true? Why it's now this one was easy. This one I somehow want to avoid doing complex analysis in this case. Not because I have an aversion to it or anything like that, but because we want to do things in Euclidean space, and there the complex analysis gets complex, and sometimes it's impossible to do. So how can I this is something I think if we could assign in a first year complex variable course, and you'd be able to do this. But you have to do those contour integrals and all that stuff. So let's do it another way. So let's write down what the Fourier transform is. Fourier transform here, so this is f of gamma. F of gamma is equal to, by the way I've defined things, the integral of e to the minus I r t squared e to the minus 2 pi I t gamma dt. So if I look at the derivative of that baby, I can integrate under the integral sign here without being incorrect, because this function decreases so quickly. F prime of gamma is equal to, well, that's still going to be the same, and I'm going to have a minus 2 pi I gamma, and then the integral e to the minus 2 pi, e to the minus pi r t squared. So I've just differentiated this, and I get e to the minus 2 pi I t gamma dt. Right? Did I do that right? Now I took the thing with respect to gamma. Oh, I get a t in there. I did it wrong. T. Sorry about that. Okay. And so now let's look at what the derivative of e to the minus pi r t squared is. Well, d dt of e to the minus pi r t squared is equal to minus 2 pi r t e to the minus pi r t squared. And so what I have here is I've got this part of that previous integral. So if I divide the rest by minus 1 over 2 by 2 pi r, what I have is then I've got this is equal to, I shouldn't skip too many steps here because I would easily make mistakes, but I divide it through, and so I have an I over r. I've got my t, that's equal to this, so I have the integral of d dt e to the minus pi r t squared e to the minus 2 pi I t gamma dt. Right? And now, when in doubt, it's begging us to integrate by parts here, right? So let's do integration by parts. So this is equal to I over R. And now I've got, here's my U, and here's my dV. So I'm going to have a V, which is e to the minus pi r t squared, and then U, e to the minus 2 pi I t gamma. I'm going from minus infinity to infinity. And then I have a minus the integral. And then I've got my V, so that's e to the minus pi r t squared. And now I've got my du, so I have e to the minus 2 pi I t gamma times minus 2 pi I gamma dt. Well, we're really lucky here because the Gaussian decreases so quickly. This is 0. So this is equal to I over R. The minus signs kill each other. I have 2 pi I gamma. And lo and behold, that's just f of gamma. So this is equal to minus 2 pi over R f of gamma. Well, this is the differential equation that we solve in our undergraduate courses. F prime of gamma is equal to minus 2 pi R f of gamma. Calculus made beautiful or something. Now I forgot my gamma here. And so that solution, from the way you solve it in wherever you went to school to take undergraduate differential equations, that solution is therefore f of gamma is equal to c e to the minus pi gamma squared over R. And I'm just for the sake of finishing what I wanted to do tonight, of all of the introduction, I'm just saying that computing that constant c is easy. It comes down to being able to solving this problem. If you can compute this, then you can solve for c. I mean, let gamma equals 0. If gamma is equal to 0, then you've got f of 0 equals c. So there's c. What is f of 0? F of 0 is just the Fourier transform of f at 0. Well, that means it's just this integral here, the integral of that. Well, the integral of that you can do by change of variables to get it down to this. So I talked quickly there, but since you're going to have a video record, I didn't mind it. So once you can solve this, then you can solve the C. Well, Laplace is one of the most amazing people of all time. He was a royalist when it was important to be a royalist. He followed Napoleon when it was important to follow Napoleon. He was, whatever party was in power, he managed to gravitate to a senior position in all those parties. But besides having great political acuity, he also was a pretty brilliant mathematician. And so this is just a throwaway for him. But he did a beautiful calculation here, which in order to compute this. Because after all, That's hard to compute, right? So how would you compute that? Well, yeah, maybe, but he did it. He did it in a way that it leaves one and off. So, but and I won't do the whole thing through because I don't want to destroy your fun for you. But basically, if you look at, so let's call this number. Let's look at the square. Let's call this number a. Then a squared is equal to the integral from 0 to infinity e to the minus u squared du times the integral from 0 to infinity e to the minus b squared dv. That's equal to the integral from 0 to infinity twice of e to the minus u squared plus v squared du dv. And then you do a change of variables, you do polar coordinates. And I'm not going to run it through. But once you do polar coordinates, it falls out at your feet. So this is equal, and then do polar coordinates. It's a brilliant technique which gets rid of the transcendental nature of this function when you raise it to a higher dimension. So do polar coordinates. If you have problems doing that, come and see me. But it's really, it's just beautiful. Okay. And now, so I didn't really talk too much about the algebraic properties. I just mentioned dilation. On the analytic properties, again, I'm not going to go into great detail, but there are two properties I do want to mention. So let me go over here. Are there any questions so far? I know I'm moving right along, but I actually find this very convenient to have the fact that this is going to be available. And we'll have to discuss how that works. I don't know how that works, but we can do that during the break. Maybe. So let's talk about the analytic properties in the Fourier transform. By the way, as you can see, I'm talking quickly, but when we get to the new stuff, I know this might be new for some of you, but when we get to what is really the heart of the course, we'll slow down to a level that's assimilable for all. And that's very hard to say assimilable when you have this thing in my mouth right now. So analytic properties of the Fourier transform. Well, there are many, and as I say, if you look in sort of a standard book, you'll see them listed. And in my own book, I put them sort of all together. But a key one is the so-called Riemann-Lebesgue lemma. And it says the following. It says that if f is in L1 of R, then the limit of f hat of gamma as gamma goes to infinity is equal to 0. Okay, that's a very basic result. And it's called lemma. That usually is, as you know, an aiding result of some major theorem. Because Riemann, of all the fantastic things he did when he was studying trigonometric series, he worked on, I would say, profound problems which are still unresolved today, concerning what are called sets of uniqueness. That's for another time, but it's a very, very interesting area which I've spent some parts of my life studying. And basically one runs into cases where you have to look at certain types of sets where the Fourier transform vanishes and that sort of thing. But I can tell you right now, without going into that theory, I can tell you an open problem that if you solve, I will do my best to get you a full professorship any place in the world, but it's easy to state. And me trying my best to get you a full professorship in the world, and $1.50 get you a cup of coffee someplace. But anyhow, if you solved it, it would be fantastic. If you take an L1 function, this is what Riemann-Levé says. Well, it turns out, if you look at the class of all, and they're continuous functions too, these Fourier transforms. If you look at the class of all continuous functions that vanish at infinity, so say someone hands you this class of all continuous functions that vanish at plus or minus infinity, then what you'd like to know, one of the questions you can ask yourself is, if someone hands you one of these functions, you say, well, does that come from an L1 function? Is there an L1 function whose Fourier transform is equal to that? Can I intrinsically look at that function over here, which is continuous and vanishes at infinity, and say it is the Fourier transform of an L1 function? So that simple question is nothing. The answer to that is nothing. Needless to say, people have tried to solve it, but that doesn't mean it can't be solved. Okay, that's the Riemann-Levé limit. Another fundamental result is the following. And I'm only going to state one direction of it. But there's a comparable result on the frequency side. So, time differentiation. So suppose that Fm, nth derivative, m bigger than or equal to 1, exists everywhere. And the reason I'm saying, for those of you who've had real variable, I'm saying it exists everywhere is I'm hiding something a little subtle here about absolute continuity. But suppose it exists everywhere, and Fm belongs to L1. Also assume that f of plus and minus infinity is equal to f prime of plus and minus infinity equals all the way up to fm minus 1 plus and minus infinity equals 0. Now, first of all, what I mean by f prime at plus or minus infinity equals 0 means that the limit of f prime of t as t goes to plus infinity, and the limit of f prime of t as t goes to minus infinity is equal to 0. Okay? And the reason I make this funny assumption is there's an integration by parts argument in this proof that I don't know how to avoid using. So assume that. Then, if I look at the Fourier transform of Fm, after all, it exists. I'm assuming it's an L1. And its Fourier transform is equal to 2 I gamma to the m f of gamma. We call it f hat is equal to that. So I can, if I have a derivative here, its Fourier transform goes into a polynomial of this type times the Fourier transform of the original. Now, remember from the Riemann-Levé grammar that the Fourier transform of anything goes to 0. So that says that if I have smoothness over here, if I got a function that's really smooth here, then I know that this baby here goes to 0 by Riemann-Lebesgue. And so that says that if I have a smooth function, which is f, with m derivatives, that says that the original Fourier transform has fast decay. This is a significant property of the Fourier transform. Smoothness on one side gives rise, gives rise to fast decay on the other side. This result also helps in the thing I said very early in the lecture, where I said that one of the reasons that transform theory is important, in particular Fourier transform theory, is because you can change from differential equations into algebraic equations. Because voila, here if I've got a differential equation, here I'm just in one variable with a derivative, I've extricated the original transform, and I've got a polynomial here. So you can imagine that I'm changing my original differential equation into, and I want to solve for f, into f times an algebraic equation. Now, in one dimension, that's not so difficult. You can imagine having manifolds in higher dimensions when you're dealing with partial differential equations, and those zero sets can lead into problems in algebraic geometry and the no-Stubben-Satz and all that sort of stuff. But that's the general idea. Okay.
I have a question.
Sure.
You
Yeah,
had
please.
mentioned uniform continuity, was it?
Absolute continuity.
Absolute continuity.
Yeah. By the way, Fourier transforms of L1 functions are uniformly continuous.
Uh-huh.
But they're not only continuous, but uniformly continuous. But when it turns out, as I said, I don't want to get into it because it's a little bit subtle, but if a function, if its derivative exists everywhere, then you can use certain arguments depending on absolute continuity to do things.
And is that an additional assumption on that?
No, I don't have to make it. Oh,
okay.
This exists everywhere is buried in there.
Okay.
Okay, so those are two analytic properties of the Fourier transform. Another property, which is very important, deals with convolution. So, how about if I go until 7:30? Well, is it safe to say you don't want to listen to me for 2.5 straight hours? That's safe to say. Okay, you have much bigger and stronger than I am. So why don't we stop at 7:30 for like 5 minutes, and then we'll come back and. So convolution. F star g of t is equal to the integral f of t minus u, g of u, the u, and if you make the change of variables, that's equal to f of u, g, t minus u. So, convolution arose in the 19th century basically to deal with differential equations. And you can convince yourself that what's going on is interesting geometrically by considering sort of baby functions. But one of the things that's really going on is something algebraic. I couldn't make these change of variables this way and have such a pretty change of variable if the real line were not a group. And basically, as I say, algebra and geometry play a very big role in this subject at almost every level. But basically, this is one of the places where I really need to tackle in dealing with a group. And that just happens all the time. And that's one shot. And there's a very basic result, I'll call it a theorem, that says the following. Let f and g be an L1 of R. Now, since I said a group, I can actually define this baby on any locally compact group. it makes sense. Because there's something called a harm measure, which is like the vague measure or any locally compact group. We're going to do even more. I'm not trying to snow people who are not interested in that, but I know there are people who know other things, and I just want to keep everyone sort of happy. Well, it turns out that then, if I look at F star G, and F star G is in L1 of R, and not only that, R is not only a locally compact group, it's a locally compact leading group. And that makes the Fourier analysis a little bit easier. So F star G has its Fourier transform, F times G. So this is another one of those fundamental properties if you're thinking of playing this game of solving partial differential equations, say. But it's also something that tells you something spectacular about the algebra going on. What it says is that we know if I add two functions in here, then it's going to be in L1. By Hurl's inequality, by Minkowski's inequality. This says that convolution is a multiplication. So this says, for those of you who have some algebra, that L1 of R is a ring. Now, if this sort of annoying delta measure were actually an L1 function, then it would be a ring with unit. The delta doesn't work that way. But this is L1 of R is a ring. And it becomes what's called a Banach algebra. There are some very significant problems that arise there. For our purposes right now, it says that if I take any two L1 functions and I multiply them with this convolution, it goes into the product. Actual point-wise product. I mean, remember, F and G are both continuous functions that vanish in infinity by our buddy Riemann-Leibniz. This convolution, which is convoluted, the word is chosen accurately, it sends under the Fourier transform into ordinary point-wise multiplication. F of gamma times G of gamma. It's really quite remarkable. Now, it's remarkable for differential equations because it turns out that if you take a differential equation, some very, very complicated ones, you can write them down as convolution equations. And if you've got a convolution equation and you take its Fourier transform, then you can write it down as an algebraic equation and extricate the guy you really want times a polynomial. So I'm not lying to you, although I think I'm probably saying it too quickly. But you can hear it over again if you want on this recording. So we're going to use this for other reasons, but this was a driving force in the 19th century for doing this sort of thing. Okay. Now, I just said that L1 is a ring with that multiplication, but it doesn't have a unit. I could prove that to you, but I shan't. That there is no L1 function, u, that does not exist, u, in L1 of R, such that for all f in L1 of R, u star f is equal to f. Well, let's prove. Why? And the answer is not, why not? Well, if I take the Fourier transform of this, we have, if so, by this result here, we have that u hat times f hat is equal to f hat. Suppose I take an f whose Fourier transform never vanishes. I can do that, the Gaussian, for example. So take f such that f hat is never 0, then u hat equals 1 on r hat. That contradicts Riemann-Lebesgue. Contradicts Riemann-Lebesgue. So this algebra, this ring L1, does not have a unit, I just proved it. So what you'd like desperately is to have a unit. And in order to resolve that to the extent one can, I mean, an honest person, we introduce the notion of an approximate identity. So definition. Kn in L1 of R is an approximate identity. For L1. If following conditions hold. For all n, the integral, it's just melting in my hand up here. It's not because I have little fingers either. Sometimes it gets very moist. For all n, kn is equal to 1. 2, there exists some constant c such that for all n, the integral kn is less than or equal to c. By the way, I'm saying something you all know, but quantification is very essential here. I mean, I wrote there exists a c, that's before the n's, such that for all n. And then 3, for every epsilon bigger than 0, the limit as n goes to infinity of the integral when t is bigger than or equal to epsilon for the absolute value of kn of t dt is equal to 0. So remember what I said when we talked about the delta. I said, boy, wouldn't it be great if we had an L1 function that was 0 every place except at the origin, and its integral existed, it was equal to 1. Because if we'd had that, then some of the baloney I mentioned at the beginning, which allowed me to motivate the inversion formula, would actually be true. This is saying let's do that, because what this is saying is I've got these functions and they're all integral as 1, and they have the property that if I exclude little neighborhoods of the origin and I look at the limit of these integrals, it's 0. So that means outside the neighborhood of the origin, everything goes off to 0.
So for example, that the Gaussians with variance power.
There are lots of examples, and that works. But one example is the following. Can you get this? Or you want to get this? Or you're throwing in a towel? It was a good idea for the first 15, 20 minutes, maybe. So example, let k be in L1 of R, where k, where the integral of k is equal to 1. And then let's look at then these guys here, k lambda, is an approximate identity. Well, first of all, I've got, by the way I define my dilation as lambda k of lambda times t, the integrals are all going to be 1. So I get this and this automatically. And then for the third one, you can prove it, we've got a plethora of examples. Just take any function whose integral is 1 and look at these dilations, and that's an approximate identity. Okay, so let's do a couple more things. And one of the things we're going to do is we're going to see how we can use this definition in the following result. I guess I can erase Nate's email. I don't want to have anybody know it. All gone. So, theorem. Let F belong to L1 of I. So if Kn is an approximate identity for L1 of R, again, this definition that I just wrote makes sense for any closely compact identity. If Kn is an approximate identity for L1 of R, then the limit of that L1 norm of F minus F involved with Kn is equal to 0. In fact, I can replace the L1 norm by any LP norm, but we don't have to get into niceties right now. So if there was really a unit, that would say that F was equal to that, but we know L1 doesn't have a unit. What we're saying is that we can come up with lots of these sequences of approximate identities where things work. And if you're just getting into the subject, you might say, well, so what? But it turns out it's a very useful technical tool. And one of the features of that approximate identity is the following. B, the limit as n goes to infinity of the integral of f of t minus the integral n over 2 pi minus m. This is going to seem strange here because I'm skipping something, but I'll explain. I'll explain in just a moment. Of 1 minus 2 pi gamma over n of f hat of gamma e to the 2 pi I t gamma. So we've got d gamma here, dt is equal to 0. Okay, so it turns out that once I have this result here, what I'm looking at here is a special approximate identity. Basically, this is a triangle. And this is a product of a triangle. See, in the triangle, I'm only looking at where it's non-zero. So this is this triangle here. And it's a maximum 1. And it's going out to n over pi, n over 2 pi. Right? Because I'm taking the absolute value again. And then it's 0 elsewhere because I'm cutting off the integral. Here, I've got this triangle times this function here. So I've got a product of two Fourier transforms. And I'm taking its inverse Fourier transform. And I'm hoping that that is equal to f of t. Well, for the triangles, the linear splines there, that's true. So, so this is a special case of dealing with an approximate identity. And I realize I'm maybe talking too fast right now, but this comes from an approximate identity. So this is true. Now, if you believe this, and I'm really not, and I don't want to be facetious here, because I know I left out some details here, but it is an approximate identity. This is of the form f star kn for a certain kn. Then what we have is the following. B implies C, which is that it's a uniqueness result. And it says the following, that if f hat equals 0 on r hat, then f is the 0 function. And you can see that item C here follows from item B, because if f hat is equal to 0 on r hat, then all I have is that the integral of f of t in absolute value is equal to 0. So that means that f has to be a 0 function. Now, we had to work very hard. I mean, I left out the whole proof, of course, but in order to get all the details in, you have to work very hard to get that. But it's sort of an amazing fact that you get uniqueness, but you get it by paying a heavy price of work. If the Fourier transform is 0, you'd like to automatically say, oh yeah, that comes from the 0 function. But in order to prove it, we had to do something complicated, do approximate identity, da 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 da. Now, why is uniqueness important? Well, uniqueness is always a desirable trait. But if we look at our paradigm for solving differential equations, it's really important. Because what if I have this complicated differential equation, and I do all my Fourier transforms, and I go over here, and I solve the algebraic equation I get with it? Well, I really want that inverse transform to be the solution of the differential equation. So that wouldn't be the case if I didn't have uniqueness. Okay, so I can kind of see my watch here. I'll cover in white, but it is 7:30. So why don't we take, but not long, but just 5 minutes. Okay? Is that okay?